Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. I want to discuss with you this really fascinating paper, extremely detailed, and as we see here from the title, Structure and Circulation of Atlantic Water Masses in the St. Anna Trough in the Kara Sea. A whole bunch of researchers involved with this. The lead researcher, PI, Alexander Osachiev, along a whole bunch of other folks, including our good friend Igor Semiletov. Okay. Now, a lot of the videos I have discussed with you have been looking at the Arctic Ocean in a basically kind of a broad manner. The Atlantification of the Barents and the Kara Sea, the heat being brought in, and then the overall effect. This paper kind of narrows in on what's happening in this specific location, the St. Anna Trough in the Kara Sea. But as we're going to see, this does tie into overall what's happening in the Arctic Ocean. Now, as I said, this is a very detailed paper. I will leave the URL link in the comments section for those who wish to explore it further. The inflow of warm and saline Atlantic water from the North Atlantic to the Western Arctic is provided by two branches, namely the Fram Strait branch water and the Barents Sea branch water. Now, throughout the paper, when you see FSBW, that's the Fram Strait branch water, and BSBW is the Barents Sea branch water. So you see those acronyms throughout the paper. The pathways of these branches merge at the St. Anna Trough, and then both branches propagate eastward along the continental slope at different depths, however. As a result, the local interaction between these branches in the trough affects the properties of the large-scale Atlantic water flow to the eastern Arctic and the deep Arctic basins. Okay? That's important there. As a result, the local interaction between these branches in the trough affects the properties of the large-scale Atlantic water flow to the eastern Arctic and the deep Arctic basins. In this study, we report extensively in situ measurements with high spatial coverage. 56 hydrological stations organized into 7 transects in the St. Anna Trough, obtained in August and October of 2021. Based on these data, we reconstructed the thermohaline structure. Okay. So that's obviously temperature salinity structure through the water column. And circulation in this area obtained new insights which are crucial for the assessment of the interaction and heat balance of water masses in the trough. First, we state that the majority of the Fram Strait branch water is recirculated in the trough within the stable cyclonic gyra. Okay? Cyclonic gyra means it's counterclockwise, while a smaller fraction returns to the continental slope. The formation of this gyra increases the residence time of the Fram Strait branch water in the trough, decreases the intensity of water and heat exchange between the trough and continental slope. So what this is telling us is that you have this warm water. If it increases the residence time, it's going to give more time for that warm water to, you guessed it, melts the ice, prevent the ice from forming, more heat diffusing to the atmosphere. as opposed to going to the continental slope where the heat will take longer to make its way to the surface and to the atmosphere, if that were the case. Second, we described the dynamic interaction between the northward flow of the Barents Sea branch water and the surface layer. It causes intense transport of warm surface water from the Kara and Barents Seas adjacent to Novaya Zemlya toward the continental slope, and it's mixing with the Barents Sea branch water along the eastern part of the trough. Okay. As we'll see later, the Fram Strait branch water is deeper in the water column. The Barents Sea is shallower. The Barents Sea branch water is shallower. So what they're saying is it's bringing some of this heat here, and it's bringing that warm surface water from the Kara and Barents Seas, which are becoming Atlantified, to the Novaya Zemlya area. And recall, I did a video discussing that whole process of the Atlantification of the Barents and Kara Seas. So that's part of what they're referring to there. These processes result in increased surface temperature at the eastern part of the trough, which enhances ice melting at the study area, increases the duration of the ice-free period. Right there. Enhances ice melting, increases duration of the ice-free period. So that's basically their abstract. Okay. Let's take a look at some of the introduction here. The large-scale transport of Atlantic water from the North Atlantic to the Arctic Ocean is among the most important drivers of the Arctic thermohaline structure and circulation. The Atlantic water enters the Arctic Ocean along two pathways, namely through the Fram Strait at about 3 to 4 Sverdrups and the Barents Sea at about 1 to 3 Sverdrups. The southern branch of the Atlantic water experienced significant transformation in the Barents Sea. The resulting cold, less than 0 C, and dense Barents Sea branch water, right, there's the acronym BSBW, flows northward to the continental slope adjacent to the Nansen Basin, mainly through the St. Anna Trough. The northern branch of the Atlantic waterway propagates eastward from the Fram Strait along the continental slope. Comprehensive review of the spread and transformation of Atlantic water in the Barents Sea and along the continental slope is given in Dmitrenko et al. In 2015. So I'm going to first describe for you the figure description for figure 1, then we'll enlarge. Figure 1A, that would be this here. 1B is this here. A map of the St. Anna Trough and the adjacent areas of the Barents and Kara Seas, illustrating general circulation scheme of the Atlantic water, including flows of the Fram Strait branch water, which are the red arrows, and the Barents Sea branch water, which are the blue arrows. And then their joint flow along the continental slope eastward from the trough, and that's indicated by a black arrow. FJL, Franz Josef Land, right? VI is V's Island, and UI is Ushakov Island, are indicated. And then B, location of the hydrologic stations in the St. Anna Trough in August are the red circles and squares, and then green circles and squares are in October. Red and green circles indicate stations in the central and western parts of the trough. Red and green squares mark stations in the eastern part of the trough. Okay, let's take a look. So here's the flow of the Fram Strait branch water, and you can see this little cyclonic flow that was mentioned earlier. This is the area within this black rectangle is St. Anna's Trough. Okay. Here is the branch water from the Barents. So the Fram Strait's over here. So they split, and then they join up right here at this black arrow. And now, if you look at the topography, right, the white to the light blue are shallow water. Then we get to, down to 7,000 meters. And as we can see, we can see the 3,000 isopleth line there. But you can see, and you see how these the topo lines are very close together. There's your continental slope. So this is all shelf, the lightly colored areas. Then here's the slope itself. Continental shelf, continental slope going into the basins. And the flow goes right all along following that continental slope. So here's the Barents and the Kara Sea, the Via Zemlya, right? I discussed how these are being Atlantified in the prior video. Now, looking within this trough region is what this figure is. And these numbers here are station numbers, right? But you can see all the green, that's the October measurements. And then all the red, you can see, makes kind of like a zigzag transect. Those are the measurements done in August of 2021. These were done in October, the green of 2021. So this kind of gives you kind of a lay of the land, right? You can see it here, August 2021, October 2021. So this kind of gives you able to envision what's going on here. And as I said, this is that little bit of cyclonic gyre that was being mentioned earlier. So this gives you the idea of the study area. And right here are the two islands, Ushakov, V's Island, right? There you go. Okay. Let's return to the text itself. Once the northern flow of the Atlantic water reaches the St. Anna Trough, part of it enters the trough along the western flank, reverses in the trough. I just showed you that, the red arrows, then exits along the eastern flank. That flow is referred to as the Fram Strait branch water, is significantly warmer, greater than 2 degrees C in the core, less dense than the Barents Sea branch water, excuse me. The Fram Strait branch water circulates in the western and central parts of the trough, while the Barents Sea branch water forms an intense northward flow along the eastern flank of the trough. And we just looked at that here, right? It goes right like that. And there's that little cyclonic aspect. Further northward at the continental slope, the Barents Sea branch water, a little dyslexic there, significantly deepens and becomes vertically aligned with the warm Atlantic water originating from the Fram Strait. Now, there's one other thing. The Barents Sea branch water forms 10th north of flow along the eastern flank. The Barents Sea branch water flow is in geostrophic balance, and its velocity depends on baroclinic and barotropic pressure gradients across the eastern flank of the trough. Okay, we need to sit there and discuss those terms. Geostrophic balance is something that we see in fluid dynamics, especially in the oceans. Now, I talk a bit about this. I didn't mention baroclinic or barotropic in my rotating systems video, but I did talk about geostrophic balance. In my rotating systems video, I go into great length into these topics. If you wish, you can check out that video. But Geostrophic balance. Let's take a body of water. You've got differing wave heights because of wave action, tidal forces, so on. Well, if I take a layer, it doesn't matter where the depth is, it could be 50 meters, 100 meters down, whatever. If I take a layer, the differing heights, the higher the water column is, the more pressure that is exerted on that layer. And the lower that water column is, the less pressure. Well, there's a tendency for things to flow down the pressure gradient. So in other words, if I look at now from the top and I got all these different pressures because of differing wave heights, the thinking would be that, the flow is to go down the pressure gradient that is perpendicular to the pressure heights. However, because Earth is a round object, lots of fluid, and it is rotating, you need to balance the pressure gradient along with the Coriolis and vorticity. And as a result, the flow is not down perpendicular to the pressures, the flow is parallel. In other words, it flows parallel to the pressure gradient, not perpendicular to it. That is what's meant by a geostrophic balance, that the flow is parallel to basically the isobars, right? Isobars are lines of equal pressure. The flow is parallel, not perpendicular to the isobars. That's what's meant by geostrophic balance. That is really, in a lot of ways, what drives and keeps perpetuating oceanic gyres. Now, velocity depends on baroclinic and barotropic pressure gradients. Okay. This ties into whatever the density of seawater is. If the pressure gradients are parallel with whatever cline you have, halocline, thermocline, pycnocline, if the pressure gradients are parallel with, let's just pick one, pycnoclines, that's barotropic. If the pressure gradients intersect the pycnocline, that's baroclinic. More broadly speaking, if you have say, isotherms or isopycs or isohalines, right, lines of equal temperature, density, or salinity, barotropic pressure gradient, barotropic situations when the pressure gradient is basically parallel with the isopycs, right? Paroclinic is when the pressure gradients intersect. Doesn't even have to be perpendicular, just simply intersect the isopycs. So that's what is meant here. Barotropic is a lot easier to analyze. Baroclinic gets challenging. But I hope I didn't confuse the crap out of you guys, but that's basically what it comes down to. Geostrophic balance is the Coriolis and the pressure gradient being in balance so that the flow is parallel to isobars, not perpendicular. Barotropic is a situation where the pressure gradients are parallel with isopycs, isotherms, what have you. Baroclinic, the pressure gradients intersect the isopycs, the isotherms, isohalines, etc. That is the most straightforward way that I can sum that up for you. Atlantic water that exits from the trough to the continental slope plays an important role in the formation of the halocline and deep layers over a wide area in the Arctic Ocean. Now, the Arctic Ocean is not a very large body of water. However, the physics is extremely dynamic, and the halocline is rapidly changing. And not only is it rapidly changing over the years, it rapidly changes within the year. There are major seasonal differences in the halocline. The halocline will be at different depths in the summer and the winter time. And this is changing, and it's constantly changing. And when you got inflow through the Bering Strait, you got inflow through the Fram, the Barents Sea, right, bringing in the warm, salty water. This is all going to affect the halocline. And if it's affecting the halocline and where it's found, it's going to affect flow. It's going to affect heat exchange. And that's the main thing. We're looking at the heat. The local interaction between the FSBW, BSBW within the trough, i.e., momentum and heat exchange, can strongly affect the properties of the Atlantic water, which flows further eastward along the continental slope. I showed you that in Figure 1, the black arrow. Okay? This affects, in turn, the halocline, and the halocline, therefore, affects the deep layers. Therefore, understanding of the interaction and transformation of FSBW, BSBW in the trough is crucial for Arctic studies, especially in relation to the ongoing Atlantification of the Western Arctic. And a couple of papers cited here. Igor Polyakov, a really good friend of mine, and he's an excellent researcher. And his 2017 paper is an extremely important one. Ask him for a reprint so I can discuss that. Previous studies provided baseline information about the structure and circulation of water masses in St. Anna Trough, a whole bunch of citations. However, the in situ measurements analyzed in these studies were limited to 1 to 3 zonal transects across the trough during certain years. Also, a mooring station at the eastern part of the trough. In this study, we analyzed the new set of thermohaline measurements obtained at 56 stations in August and October 2021. These measurements covered the central and southern parts of the trough with high spatial resolution and provided new insights into one, the circulation of FSBW in the northern part of the trough, two, interactions between the BSBW and the mixed surface layer. We will see that abbreviated as MSL in later diagrams along the eastern part of the trough. The obtained results are important for the assessment of the interaction and heat balance of Fram Strait branchwater, Barents Sea branchwater, halocline, mixed surface layer in the study area. Okay, data and methods. The St. Anna Trough is located in the northwestern part of the Kara Sea between Franz Josef Land to the west, the Via Zemlya to the south, and Vis Island and Yushakov Island to the east. We show that in the first figure. The trough is oriented from south to north, about 500 kilometers long, with a relatively stable width, about 150 kilometers. It has relatively plain relief, 500 to 600 meters deep. In other words, flat bottom, okay, in the southern part, and 500 to 700 in the northern part, bounded by steep western and eastern slopes. Okay, that's figure 1B, which is right here. And you can see it, right? It's shallow here, gets very deep, shallow here, and gets deep. And this is the deepest part. When you can see the 500 meter level indicated there. Right? Again, a review. Red is the Fram Strait. See the little cyclonic bit there? There's the Barents. Okay, the red and blue is just to differentiate the two. Does not necessarily mean indicating any temperature, although the Fram Strait is warmer waters. And then the black is where you can see they join up, continuing along the slope. Okay. Just a little a review and for reference there. Okay. Sea depths westward and eastward from Trough are less than 200 meters. We saw that. In the south, the Trough is connected with the shallow central part of the Kara Sea, about 50 meters, and the northeastern part of the Barents Sea, 150, 300 meters, 350 meters. In the north, the Trough crosses the slope and connects with the deep Nansen Basin, which is 3 to 4,000 meters. So, think of a big old swimming pool. We got the shallow end and the deep end. In this work, we analyzed the in-situ measurements, right? We talked about the transects and so on. During both cruises, the vertical thermohaline structure was investigated using a conductivity temperature depth instrument, CTD. We could not do physical oceanography without CTDs. Yeah, we also use flow meters and stuff like that. Flow meters are usually easier to do at the surface, but and of course we've got you know ROVs and that kind of stuff there. But really, the main instrument are the CTDs. We just drop it, so we get a vertical profile at that location, and then when we do transect, we then get the horizontal aspect. You take all this data and you can create these transects, and you create these figures of, along this transect from let's say this longitude to this longitude, or this latitude to this latitude, we can see the structure of the ocean, however hundreds or thousands of meters down. CTD is invaluable. This is how we do physical oceanography. And they say seabird electronics 911 plus, okay, and a 24 hertz sampling rate, whatever. And give further descriptions of the unit, fine. The heat content in different water masses in the study area was calculating using the formula H for heat content is equal to rho sub 0 times C sub P, and we integrate from Z1 to Z2, and what follows the integration sign is theta minus theta FR dz. Okay, Z1 to Z2 are the different depths. So you're integrating vertically from one depth to the other. It could be from 50 meters to the surface. It could be 150 meters to 70 meters, wherever you choose it. And that's going to what's going to determine that is what are the indication. Oh, we see a strong thermocline here, or we see some noticeable change here. So you can calculate this across. So what are the various variables here? Theta is the potential temperature, basically the temperature at depth. Theta sub FR is the freezing temperature. Now, it's not 0C. We have salty waters here. Freezing point depression. It's going to be less than that. Typically in the Arctic, on average, roughly speaking, it's about minus 1.8, thereabouts. So that would be a freezing temperature. And P sub 0, that's your density, is about 1,027 kilograms per cubic meter. That's your seawater density. That is an average. And CP is the specific heat capacity. And it's given as 3,000, almost 3,992 joules per kilogram per degree Kelvin. What was to say per Kelvin? Okay. Now, if you look at the units here, okay, I've got density, kilograms per cubic meter. Okay, now look at the specific heat capacity. I have joules per kilogram. These are multiplied. So therefore, the kilogram over kilogram, they cancel. Okay, so they cancel there. So that cancels. And then we're talking about temperature differences here. So you're going to calculate a temperature here. So you're going to have temperature in the numerator. Well, you got temperature, it's temperature over temperature. So the temperature units cancel. So what are you left with? You are left with joules per cubic meter for your heat content. So you're going to integrate that over the column. So you're going to get joules per cubic meter, and then you multiply by the volume of your area to get the total heat capacity. So that could be simple things like, this many, difference in latitude, this many differences in longitude over whatever depth you were integrating over, and you get your XYZ, and you've got your volume. Okay? One thing I always, when I was teaching and when I was doing my research, one thing I always stressed was work the units out first. Make sure you end up with units that make sense. If they don't, your setup is incorrect. So you're going to end up with joules per cubic meter. Makes perfect sense. And again, Lyakov, 2017. Satellite maps of sea surface distributions of corrected reflectance and brightness temperature in the study areas were retrieved from MODIS satellite data. These data were used to address certain aspects of the surface, circulation, and St. Anna Trough. And they go on to describe some other aspects of their methodology. Okay, let's take a look at the results now. The Fram Strait branch water. The vertical structure and salinity structures observed along the transect in the St. Anna Trough in August 2021 is shown in figures 2 and 3. It demonstrates the presence of the main local water masses, namely mixed surface layer, halocline, Fram Strait branch water, Barents Sea branch water, especially noted in figure 4A. A mixed surface layer, salinity less than 34.1 because freshwater input, and a more saline and dense halocline, 34.1 to 34.7, occupied at depths from the surface to about 50 to 70 meters. Another water mass is referred to as an MSL mixed with Barents Strait branch water, which is significantly warmer than the halocline. And the temperature is 0 to 2.5 C in August, minus 0.5 to 1 C in October, but more saline than the mixed surface layer. Okay, that makes sense because the Barents Sea is going to have a higher salinity. The mixed surface layer has a low salinity. You're going to mix that. You're going to arrive at an intermediate value. So let's just take a look. Yeah, as I said, if anyone wants to read the nitty-gritty details, just pull up the URL. Let's take a look at figures 2. Vertical temperature structure along the transect A2 to A6. And the red station numbers indicate locations of the Fram Strait branch water cores. Now, a reminder, just blew right past it. Here are your transects, 2, 3, 4, 5, 6. Right? For that, there's your transects. So this way you get an idea of what they're showing. So let's take a look at this. Okay, so here's transect A2, A3, A4, A5, A6. And you can see here, now this is the distance, right? Here's your temperature. Now these are actual temperature. These are not temperature deviations from an average. These are the actual readings. Okay? So you can see slightly cooler. This is this very thin bluish layer. That's your mixed layer. Then you can clearly see this warmer water that's present. And it gets slightly cooler, and then we're starting to get more into the cooler waters here. And as we go through these transects, we see basically the same thing. Now, when we get to 400 to 600 meters, so this is where we're getting into slope water. Slope water, we expect it to be cooler. So what we're seeing here is we're seeing, the Fram Strait water up here because it is warmer, right, as described in the text, and just underneath that, in the, I guess, more orangey, but right about here, probably some of the Barents Sea water, and then we get into other intermediate waters. But we can clearly see its presence. Clearly see it. Okay, let's look now at the salinity, vertical salinity structure. Okay, take a bit of a peek at that. Again, we can see, and the darker the colors, the more saline it is. And you notice that it's going from 33.5 to 35, only a difference of 1.5 practical salinity units. But as I keep trying to stress, it doesn't take much difference in salinity to drive thermohaline flow. It really doesn't. But what we see here, we see that mixed surface layer right up here. This is where we see some of the lowest salinity values. Makes sense. We got freshwater input. Could be from the melting ice. Could be from precipitation, right? There's your fresh riverine input, right? We got the a fresher water signal here, and then we can see you can see a very strong signal of that intermediate water right here, basic 35 parts per thousand practical salinity units right here, and we can see that persistent in the first two transects, which is closer to the, I guess we call it the mouth of the trough. In other words, closer to where the slope is, and that is definitely clearly the Fram Strait water, the Fram Strait branch water. So we clearly see its signal in the first two transects, and then we start seeing slightly lesser salinity values, which is reflective of the Barents Sea branch water, but not by much. So just a reminder, those right, A2, A3, right, these transects right here, that are right here, that's showing very clearly the Fram Strait branch water. And then when we get down to here, we see slightly lower, not by much, but slightly lower salinity value that's reflecting the Barents Sea branch water. So we clearly see the signals in looking at those figures there. Right, we see this is temperature. We see the warmer signal of the Fram Strait. Then you can see it gets cooler with these different transects because the Barents Sea is slightly cooler. Again, not by much. And then for the salinity, very strong Fram Strait branch water signal, and then slightly lesser salinities indicating the presence of the Barents Sea branch water. And here's that mixing, that intermediate value between the mixed surface layer and the Barents Sea salinities. It's right there. You can see it's 34.7, 0.6 before we get into the 34.85 realm. So you can see that in between of the Barents and the mixed layer. And just like we see it up here as well, but not as thick a layer. Okay, so this is giving you an idea of the structure of what's going on in the St. Anna Trough. Now, figure 4. This is a good one. TS diagrams, temperature salinity diagrams, including the freezing point temperature, which is the magenta line, okay, and the sigma contours, gray lines, at the hydrographic stations in the St. Anna Trough at transects A2 to A6 and B transects B1, B2 in October. Circles mark measurements at stations in the central western parts of the trough. Squares mark measurements in the eastern part. Okay, take a peek. Now, first of all, okay, these gray lines that you see here, okay, these are lines of same density, isopics. Now, in oceanography, you see 26.5, 27.5, 28. We dropped the 1, 0. Remember when I showed you the integration formula? The density was like 1,027.5 kilograms per cubic meter. We dropped the 1, 0. So basically, this is 1,027.5 kilograms per cubic meter, 1,028 kilograms per cubic meter, etc. So these are similar density. So in other words, I could change the temperature, but if I also have similar changes in salinity, I can stay on have the same density. So if I increase the temperature to make it warmer, to keep the same density, I would need to make it saltier. Likewise, if I decrease, say, the salinity, I would need to make the water colder to stay at the same density. So TS curves is something that is a very handy tool that's used in oceanography. And it's usually plotted as potential temperature on the vertical versus salinity in PSU, practical salinity unit, on the horizontal. So I could say, look at a salinity of 33 and a salinity and a temperature of 1, find where they intersect, and there's my density, 1,026.5 kilograms per cubic meter. I can do that. This is the freezing point temperature indicated here. This is August, this is October. MSL, this is the mixed surface layer. As you can see, it's all over the place because it's mixed. The waters, we are mixing all sorts of temperatures and salinities. It's mixed. So we're going to see a wide range of values. Okay, but now the mixed surface layer mixed with the Barents Sea brown bottom, Barents Sea branch water, and it's right here in this red oval, and you can see it right here. There's your mixing, and this is within the halocline. We can see it right here. Boom, bang. Right? See this? Like looks like a check mark. Bang. There's your halocline. Right there. And by the way, these, right, go back to, I think, this one here. Right? There's your mixing. That's indicated right here. That's what they're showing. And then later on in October is not as, we still see it, but it's not as pronounced because, as I said earlier, the halocline is constantly changing from month to month, year to year, and so on. As you notice, the halocline, not as pronounced. We still see it. It's right there. Not as pronounced as in here. And then we see where the Fram Strait branch water is and the Barents Sea branch water are, signature-wise. And the different colored dots here are the depths at which these measurements are taken, especially referring to in these panels. A lot of these purple dots in the 0 to 30 meters. The blue dots are in the 30 to 50 meters. And then the light blue, you can then track it yourself. So there's a lot of stuff going on in the upper, basically, 30 to 50 to 100 meters. But we can clearly see the mixing here. We can clearly see the halocline. The most saline, more than 34.7 PSU, and dense Atlantic water is located below the halocline, with a distinct difference between warm Framstray branch water greater than 2C in the core and cold or cooler Barents Sea branch water less than minus 1C in the core. In this paper, we distinguish these water masses by the isotherm of 0C, i.e., BSBW is colder than that and centered at sigma 0, which is about 28 kilograms per cubic meter or 1,028 kilograms per cubic meter, while FSBW is warmer than 0 and centered at sigma 0 of 1,027.85 kilograms per cubic meter. This exact partition is somewhat arbitrary, however, it does not affect the analysis presented in the study. Basically, pick a middle point. And then they go on to discuss that thermohaline structure and the St. Anna Trough observed in August 2021 is consistent with previously reported in situ measurements in the area. FSBW is manifested by 1 to 3 cores of warm water located at intermediate depths. August 2021, we detected 3 warm cores at the northernmost transect, A2, and they give you 81.5 to 82 north. 2 warm cores at transects A3 and 4, 80.5 to 81.5 north, and 1 at A5 and A6 at 79.5 to 80.5. So basically from 79.5 all the way up to 82 degrees. So that's basically 2.5 degrees of north latitude. So that's about some 250 kilometers in distance, right? Usually a degree latitude is about 110 kilometers. So 220, well, I guess more like 270 kilometers or so. So it covers a good chunk of it. And keep in mind, this is water that's above 0, bringing in all that warm stuff into the Arctic Ocean. So they discuss some other aspects, and so they're getting into the really fine details here. Okay, I'll let you read through the details here. However, there's something interesting we need to discuss. The observed configuration of warm cores at transects A2 and 3 contradicts the circulation scheme with meandering of the alongside boundary current described by Dmitrenko in 2015, but proposes 2 new possible circulation schemes at the northern part of the trough. So, in other words, their findings seem to go against or counteracts what Dmitrenko described in 2015. Considering this is 6 years later, things could have changed. What he proposed in 2015 might have been correct, but things are constantly changing, so that now his model needs to be modified. So what they're proposing in this study is two new possible circulation schemes at the northern part of the trough. The first scheme is that the central warm core at transect A2 is the outflow of the FSBW from the trough that flows further northward to the continental slope, while the eastern core is the meander of the alongside current. The second scheme is that the eastern warm core is the outflow from the trough to the continental slope, while the central warm core is the meander from the south, which further merges with the inflow of FSBW. Note that the second scheme proposes that FSBW forms a recirculating cyclonic gyre within the trough, i.e., most of the northward flow along the eastern flank reverses and at the northern part returns to the trough along the western flank. As a result, only a small fraction of FSBW water is transported off the trough to the continental slope, while the majority remains in the cyclonic gyre within the trough. This is going to be, and if you go back to the beginning, basically they're abstract. They talk about the waters persisting within this trough that enhances ice melting at the study area. So, in other words, as they show later on, they think that the second scheme is what takes place. The majority remains in the cyclonic gyre. Some still don't get it wrong. It doesn't all stay there. Some of it does merge with the BSBW, and it does merge to move along the continental slope, but a lot of it stays enhanced, and that is a major contributing factor as to why the Barrens and the Carices are now appear to be staying ice-free longer, and why there is a delay in the Atlantification process of the Laptev and the East Siberian Seas. Now, the warm water might, not all of it, but some of it might be getting hung up in that trough, getting entrained there. So less of that warmer water can flow into the shallow. It's transporting along the slope, but may not get advected, either Ekman pumping, what have you, onto the shelf itself to further Atlantify the Laptev Sea, which is why the Laptev Sea might be persisting in staying a little on the cooler side. But eventually it will get Atlantified. It really is just a matter of time. Here we go. The location of the cores of the inflow and outflow streams at the transects A2 to 5 supports the second proposed circulation scheme, which is illustrated by the horizontal temperature distribution in a trough at the depths of 100 and 150 meters, figures 5C and D. The distance from the outflow core of the FSBW to eastern slope of the trough decreases from 60 kilometers, transect A4, to 40 kilometers, transect A3, and then abruptly changes to 60/10 kilometers, which indicates the presence of the gyre circulation. Let's look at figure 5. Horizontal temperature structure in the St. Anna Trough at the depths of A, 0 meters, B, 50 meters, C, 100, and D, 150, and they're drawing out tension to C and D. Let's take a look. So we can see that it's warmer here, and then it appears to indicate a switchover. We see some cooler surface temperatures here, 25 meters. So that's probably getting into some of the mixed layer a bit as there. And right here, we can see a reversal. There is a diagram later on that explains this better. The second circulation scheme consists of first the western inflow, eastern outflow, streams that connect the St. Anna Trough with the continental slope, and second the cyclonic gyra within the trough. Therefore, the zonal transect at the northern part of the trough can cross these FSBW streams 4 times from west to east. 1, the FSBW inflow. 2, from outside to inside. 3, from inside to outside the gyra, and then the outflow. So basically, input, it twirls around a wee bit, and then it gets spit out, basically. To check this assumption, we performed the second field survey of the trough in October, 2 months after the initial. And, excuse me, and then that was the basis for figure 1b. The vertical temperature salinity structure along the transects B1 and B2 supported the second circulation scheme, figure 6 and 7, which I'll pull up in a moment. The zonal transect indeed crossed the FSBW streams 4 times, indicated by the 4 warm cores in figure 6a. So they are now referring to like these warm cores right here, most likely. But figure 6 will show it a bit better. Note that both the southern and northern ends of transect B2 were outside the warm core, which indicates this flow is not the outflow, but part of the gyra. Okay, let's take a look at figure 6. You can see warm core, warm core, warm core, warm core. And right there, right, the center of it. Okay. And then we look at the salinity. And the black arrow, by the way, it indicates the intersections of some of the transects. Right there. And again, boom, see the cores there? 1, 2, 3. Got the cores. So 34.83, what, 34.86, 34.86 kind of tells you it's spinning around something. I think the salinity shows it better than necessarily the temperature, right? Here's the intersection there. But the salinity, which makes sense because things in the Arctic are driven more by salinity differences, right? 34.86, 34.86. This is obviously, and then something in the middle here. So this is obviously, this is looking at it from the side. So just imagine if, water's coming at you, then going away from you. But something is definitely spinning here. So yeah, this to me better indicates the gyra that they're discussing. Okay, continuing on. To verify the presence of the FSBW gyra, to visualize the general circulation scheme, we calculated geostrophic currents in the trough based on the thermohaline measurement data. And they looked at the baroclinic and the barotropic components. And then they cite figures 8 and 9. The zero velocity level for the baroclinic component was prescribed at a depth of 30 meters. That is below the mixed surface layer and above the Atlantic water inflow. The geostrophic currents were calculated only for the transect that they did. Okay, so then they talk about the sum of baroclinic and barotropic components of the geostrophic current along those transects. Note that the current velocity is shown perpendicular to the transect lines. These are your transect lines, and the white dashed line indicate isotherms. Okay, so let's take a look at figure 8. So here we get the velocity. Now, when you look at the velocity, let me see if I will enlarge it yet. You see the minus 10, the minus 5? Velocity, remember, is a vector quantity. It contains not just scale, not just magnitude, but direction. So the minus value is just simply telling you a direction. It could be west, and then positive could be east, or it could be south, and positive could be north, whatever. But the negative simply tells you direction. So when you see the 0 indicated here, okay, there's no velocity there. So what does that mean? So now let's look at the colors here. On the, what the hell is it, like purple on this side and orangey yellow on this side here. So, but this purple means it's negative value, so it's coming at you. Over here, the positive value means it's going away from you. Coming at you, going away from you. Yeah, it's rotating. You see it right here. It's rotating. And you see some funky stuff here. But again, we can see the rotational aspect. And the minus 5, minus 1, this is obviously the Barents branch. The 2, see, that's the Fram. You can see that the Fram is a little shallower than the Barents branch. So we see that as well in these diagrams. But you can see right here, this is flowing at you, this is flowing away from you, and it's spinning around this thing here. That's your pivot, that's your axis. Right there. Very nicely done. And it shows it very clearly. And now for another look at this. So the one we just looked at was a side view. This is the top view. And these are vector arrows. Right? So you got the flow coming in, and oh, looky. See the cyclonic flow? Right there. We see it. Then they do summations. So flow this way and flow this way. So it's doing what? It's pivoting. The flow in. You notice the flow away. But right here, we can clearly see the gyro. So their data clearly supports their second proposed scheme, second mechanism for what's going on. This is like really excellent research. And they go on to describe that figure 8 demonstrates the resulting geostrophic current. We just looked at that. We just looked at figure 9. I mean, it shows it very plain and clear what's going on there. Big attempt, we don't, it's not necessary to look at that, but what they did want to look at is whether the cyclonic eddy is stationary and persistent feature or if it's temporary. And basically, what they are arriving at, their determination is that it typically is pretty much persistent. Okay, so the Barents Sea branch water in the St. Anna Trough is cold and dense, occupy the intermediate and bottom layers along the eastern flank of the St. Anna Trough. The lowest temperatures is equal to minus 1.1 and minus 1.2 C was registered in the narrow bottom layer. Okay, go back to figures 2 and 6, you know, where we saw that. I think this was figure 2 and 6. It's figures 2. So intermediate layers, they're talking about in this here, right around here, right? What they're talking about. This should be figure 6. Again, we see it here, right? So, so that's what they're referring to there. The intense northward flow of BSBW in eastern part of the trough is in geostrophic balance. That's this right here. Right? Northward flow, right? 80 to 82. Geostrophic balance following, moving parallel with the pressure gradients. And then this is where it starts to get entrained with the Fram Strait water, and then eventually it spits out combined over here. The thermohaline structure and circulation observed in August and in October agree with previous studies. The main new finding of this study related to the Barents Sea branch water addresses the mixed surface layer above the BSBW in the eastern part of the trough. The measurements showed that the surface layer along the northeastern part was significantly warmer, 1.6 2.4 C in August, and 0.3 to 0.5 C in October, a more saline 34 to 34.2 than that of the central and western parts of the trough. Moreover, the cold, less than 0 C halocline layer was thin, 10 to 15 meters, or absent. The isotherm of minus 0.5 went from raised from the depths of 450 to 550 meters to 120 to 150 meters at the eastern flank. That's a wee bit of an increase. And I think, look back at figure 2, that's kind of what they're getting at here. The observed feature, i.e., increased surface temperature at the eastern part of the trough, was reported in previous studies, demonstrated that this warm and high saline anomaly is local, i.e., not observed in the surface layer further westward or eastward. So now the question is, why is that? And Dmitrenko presumed that its formation is caused by an upward heat flux from the outflow of the Fram Strait, which interacts and mixes with the Barents Sea branch water along the eastern flank. However, our measurements contradict this assumption for the following reason. First, maximal temperatures in the core of the warm surface layer in the eastern part of the trough were the same as those in the core. The temperature of the surface layer warmed as a result of vertical heat flux should be distinctly lower than the temperature of FSBW due to heat losses between these water masses. Second, the warm and saline surface layer was located exactly above the BSBW and about 20 to 30 kilometers eastward from the FSBW outflow. We propose an alternative explanation for the formation of warm saline surface layer along the eastern flank of the St. Anna Trough. The surface temp and salinity structure show that the source of this water is located in the southeastern part of the trough above the BSBW. The temperature in the eastern part of the trough above BSBW, the temperature at a depth of 25 meter decreases from 2 to 3 C in the south to 1.5 to 1.8 C in the north. Figure 5B. 5B. That's apparently what they're getting at here. Just follow the isotherms, I guess. Where was I? In the central and western part of the trough above FSBW, the temperature at a depth of 25 meters decreases from 0 to minus 0.5 in the south to minus 1 to minus 1.2 in the north. Thus, the temperatures of the surface layer above both FSBW and BSBW significantly decrease from south to north, makes sense, while the temperature difference across the trough between east and west at the same latitude remains relatively stable. We presume that the intense northward flow of BSBW along the eastern flank of the trough interacts with the surface layer. This interaction induces first northward transport of the warm surface layer above the BSBW, and second, so basically just grabbing it and moving it along, and second, mixing of the warm surface layer with the BSBW. As a result, the salinity of the surface layer of the eastern flank of the trough increases, becoming higher than at the same longitude westward in the trough. The temperature in the surface layer decreases due to mixing, but remains higher than at the same latitude westward in the trough. The difference in salinity and temperature surface layer between central and eastern parts of the trough increased significantly from the southern transect to the northern transect. And, if we are looking at all these various transects, we see exactly what they're describing. We can see it right here, right? And then they talk about the salinity. Again, we can see the salinity. There's the mixing of the salinity. So we can see everything that they're talking about, right, in the discussion here. And there, of course, is the. So let's see, kind of reviewing Figure 5. Right, this is Figure 5. Warmer, cooler, right? So we see what they are discussing in their by looking at their the figures that they provide. Right? There's the transect. There's the temperature again, a little warmer, a little cooler. We've got some entrainment going on. So basically, over here on the eastern side, right, east-west, right, we see that some of this warmer water is mixing with some of this cooler water in this region here to get a temperature somewhat in between. And we can see this kind of a bit of an upward movement, some perhaps an upwelling following the bathymetry, but we see that. So what they say in their discussion is supported by the figures here. And these are probably the geostrophic flows and so forth. And let's see. Okay, now they got some important paragraphs here. We presume that the intense northward flow of BSBW along the eastern flank of the trough interacts with the surface layer. This interaction induces first northward transport of the warm surface layer above BSBW, and second, mixing of the warm surface layer with BSBW. As a result, the salinity of the surface layer along the eastern flank of the trough increases, becomes higher in the same longitude westward in the trough. The temperature of this surface layer decreases due to mixing, but remains higher than at the same longitude westward in the trough due to the decrease in air temperatures with the increase in latitude. Indeed, in August 2021, the difference in salinity and temperature of the surface layer between the central and eastern parts of the trough increased significantly from the southern transect to the northern transect. The proposed scheme of the northward flow and mixing of BSBW in the surface layer along the eastern part of the trough is supported by thermal satellite imagery of the study area. And they go on to discuss, looking at the reflectance and so forth. While that's interesting, I think they have really made an excellent case for what they're suggesting. They have excellent data. So let's see what they have to say in the discussion. The in situ measurements provided new insights into the circulation of the local water masses. The recirculation of most, not all, most of FSBW within the cyclonic gyre, and 2, the intense northward transport of the warm surface layer along the eastern flank and its mixing with the Barents Sea branch water. Considering the scheme, the obtained in situ measurements provide an opportunity to assess the transformation of the Atlantic water during its flow in the trough, including changes in temperature, salinity, heat content. The latter was calculated using the vertical integration range. That's the formula I showed you earlier. Okay? And they chose the depth based on the isotherms of 2C, and while for FSBW, isotherms of 2C, and for BSBW, minus 0.5C. Now, they admit it might have some bias due to potential underestimation of the maximum temperature and salinity values, as well as the heat content. But hey, you can only do so much, right? But they're at least admitting it, and they know where they need to tighten things up for future studies. And of course, like anything else, when you do your transect, you do your CTD cast, it's really just a snapshot in time. So it is a major challenge to extrapolate what it means on the long scale. But the ocean's a big place, and we do the best we can. So they discussed some of the limitations. We believe that the obtained results are representative of the circulation and transformation of the Atlantic water in a trough, so it can be used as a first order approximation of these processes. And then they show you the general circulation scheme, which is pretty much, you know, what we showed earlier. But, okay, this is the main flow of what comes into Fram Strait. Some of it branches off. Some of it gets entrained to form that gyra. And some of it spits out. The Barents Sea comes in. And all these three meet up here and flow along the slope and further down, that in the eventual Atlantification process of the entire Arctic Ocean, especially first on the Eurasian side. So, just to clarify, not the entire water coming in through Fram Strait goes in here. Just the volume alone, there's not enough volume for that. The main flow does continue this way, but there is a branch that splits off, and then it spins around here, and then before being spit back out to hook up again. It's almost like a little bit of a detour. And then the Barents Sea coming in here. And these little, kind of almost look like cyclone symbols here. They're supposed to, like little swirly durlies, they're supposed to indicate mixing between the surface layer and the BSBW. So this is indicating mixing along the way. The kind of little summation of what's happening. And they go on to say that the temperature and salinities of the warm cores at the intermediate depth, which correspond to the FSBW, show good agreement with the main circulation features, including the gyra. And they refer to it as FSBW small case G. Okay? So that makes sense. I don't know if they did. Yes, they did. They put the G in here. I didn't see that at first. So yeah, there's your gyra right there. So they did indicate that. And then they say the FSBW inflow, FSBWI, and then the southward outflow, OS, outflow south, and the northward outflow, ON. So that is this right here. So a little bit can flow that way, and then here's the outward flow to the north. So here's the input, branching off from the main Fram Strait inflow, kind of spins around a bit in there. Then we spit a little bit out to the south, and we spit a little bit out to the north. It joins up with the Barents branch and continues on its merry way. Maximum temperatures in the inflow in October were significantly lower than those in the gyra. Well, it makes sense. It's kind of cooling down, right? Including measurement in the coldest part. The depth of the temperature maximum, 105 meters, of FSBW inflow is similar to the related depths in the western part of the gyra. However, the depths of the merging shallow inflow core and the deep northern part are also consistent with those in the western part. So they're just really getting into the minutia and so forth. And then they discuss that if the fact that that the inflow flow has lower temperatures than the FSBW inflow is questionable. So they're talking. This is not clear to me. Inflow flow lower temperature than the inflow flow. What, at different times of the year? Well, that makes sense. Or is one of them supposed to be? I think one of them is supposed to be the gyra. Yeah, yeah. It's questionable because the inflow is a source of heat at intermediate depths. So what did they just say? They said that the inflow was lower than that of the gyra, and basically the inflow is the source of heat in the trough at intermediate depths in the trough. So they're basically having some questions with the data here. I see what they're saying. So there was an error in the printing. So they proposed a possible reason. The inflow of the Atlantic water to the trough is non-stationary in terms of temperature and intensity, which can result in the observed temperature difference between. Here we go. Inflow and gyres. Yes, that's a misprint there. At the only transect B1 across them. Okay. The outflow in the south is colder than the gyre. Well, if you're having heat that's diffused to the gyre because it's spinning around, that's a possibility. And they go on to discuss the Barron Strait branch water. Another little flip of the letters there. And again, they're getting to extreme minutia here, which is all fine, but it's not. I don't consider necessarily germane to why I'm featuring this paper. And they continue to discuss, the thermohaline measurements, the temperature salinity measurement, and they give further detail and they further reference other studies. But what is interesting to note is the temperature and salinity of the FSBW and the St. Anna Trough also significantly change on the interannual timescale. The maximal temperatures in the eastern part of the trough steadily increased from 1.5 C in 1965 to 1.75 C in 1994 and 1996, and 2 to 2.5 C in '08 to 2010. So, in the span of some 40 years, 40, 50 years, we went from 1.5 to 2.5 C. That was a whole degree warmer. Remember the heat content of water, the specific heat content. That is a lot of extra heat that's in the water and being carried into the Arctic Ocean. And then they go on to discuss some changes in salinity. That is very telling right there. Again, a couple of citations of Igor's 2017 2020 paper. So, what did they say about the maximal salinities were equal to 34.93 in 65 and 94, 34.95 in 96, 34.94 in '09. So it's kind of in the same ballpark. But then in 2021, we registered a significant reduction in salinity with a maximal value of 34.89. This result is also associated with the interannual variability of the Atlantic water along the continental slope in the Barents Sea. So basically, we're talking 600ths of practical salinity units. May not seem like much, but it is important. So, in the conclusions, the study describes the extensive in situ measurements in Santa Ana Trough, with specific emphasis on the northern part of the trough. Good spatial resolution provided novel information. So, they're just kind of recapping what they go on here. Based on the obtained in situ data, the cyclonic gyra has stable temperature, salinity, vertical location of the core. Aha. I mean, that's a persistent thing, persistent feature, which supports the second scheme. There's the gyra that explains what goes on. The inflow of the Fram Strait branch water from the continental slope is less saline than the gyra. So basically, the gyra is concentrating as it further entrains the salinity, while both outflows are more saline than the gyra. So the salinity just keeps increasing. Excuse me. We presume that the stability of temperature and salinity in the eastern and western parts of the gyra is divided by its recirculation and the resulting heat and saline balance with the Barents Sea branch water flow. The Barents Sea branch water core, adjacent to the sea bottom layer, has stable salinity but variable temperature within the trough. While propagating northward, temperature at the upper branch water of the Barents Sea steadily increases and salinity steadily decreases due to mixing with the warm and low saline surface layer. But the mixing does not get all the way to the bottom. So the bottom remains unaffected. The results obtained in this study are an important modification of the circulation scheme in the St. Anna Trough described in previous studies. They are important in understanding the interaction of local water masses, which determines density heat content. In particular, the presence of that gyra significantly increases the residence time of the Fram Strait bottom water in the trough. This results in decreased heat inflow from the continental slope, modifies the heat balance between the two branch waters in the trough. In particular, we did not register any evidence of intense mixing and heat exchange between the two branch waters within the trough. On the other hand, the Barents Sea branch water experienced intense heat exchange with the halocline and surface layer during its flow through the trough. The transport of warm water from the south to the eastern part of the trough affects ice formation and ice melting. Here we go. Want to know the significance of the study? Right here. The transport of warm water from the south to the eastern part of the trough affects ice formation and ice melting. This process significantly increases the duration of the ice free season. So, why did I bore you for the last 19,000 hours? Is to tell you that what happens at local locations can have wider implications for the general region. And they have a mechanism now that the gyra basically concentrates that warm water or keeps it contained so that it melts the ice, prevents the ice from forming, increasing the duration of the ice-free season. The intense northward transport of the surface layer from the northern part of Novaya Zemlya toward the continental slope could be important in the context of the freshwater balance of the Kara Sea. And they go on to talk about the Yenisei plume, which occupies a wide area between Novaya Zemlya and the continent in the central part of the Kara Sea, is among the largest freshwater reservoirs in the Arctic Ocean. Well, that obviously explains the lesser salinity values. This plume, with salinities less than 25, is formed during the ice-free period in summer and autumn, disappears during ice period, i.e. in early spring. Salinities in the central part of the sea are greater than 30. The fate of the Ob Yenisei plume under ice during this cold season remains unknown. Despite certain progress in our understanding of processes in the St. Anna Trough, many important issues remain unknown. Hint, hint, future research, future funding. Among the others, we want to highlight the question of the formation of the gyre. Right? So we want to find out why does it form in the first place. Okay, might be some topographic element on the seafloor. Okay, because they notice a reversal. Maybe it's topographic steering influence, but they're saying it's small and local. They don't know, so they're speculating at this point. So anyway, they talk about they need in situ measurements to better elucidate that issue, and they also talk about they need measurements actually underneath the ice and so forth. But what we've seen here is that there's given the volumes of the inflow and outflow, the influence of the gyre on mixing heat balance in the trough. So go back up to the top here, and let's go to this figure here. So we got the inflow from the Fram going this way. A branch splits in here and circulates. We know that the Barents Sea and the Kara Sea are being Atlantified. Right? We've got this warm saline water being brought in. The Barents Sea is warmer than it has been in the past. It's getting saltier than it has been in the past. It is still cooler than when compared to the water in through the Fram, but it still contributes to Atlantifying these two seas. So, and over here we get into the Laptev. And right now, the Laptev, we're just now starting to see hints of being Atlantified. But again, I refer you to the lengthy video I did on the Atlantification of the Barents and Kara Sea. It hasn't quite reached there yet. It hasn't, the extra warmth and higher salinity value hasn't quite gotten in there. It's getting there, but not quite yet. Well, this may explain why that. Granted, not all the water through the Fram gets caught up here. Some does go through, but if some of it does get entrained here, that's a delaying process, and that could help explain. It'd be a contributing factor as to why the Barents and the Kara Sea have readily Atlantified, because there are some, reverse flows here, but it's entraining the heat. And that heat spreads, and that heat melts the ice. That heat prevents the ice from forming. That heat keeps an ice-free season longer. So that's, by looking at this local, what's going on here, they're actually able to explain why the Laptev thus far, they didn't state in their paper here, but I am making the extrapolation. It probably explains why the Laptev has thus far not fully succumbed to Atlantification. But it will eventually. It's just that this mechanism is going to delay that process. So I think this was excellent research, and you know, they go back and look at the the temperature and salinity profiles like this here, right? You can always feel free to freeze the videos and study these, or if you just pull up the URL yourself and look at the paper. But this shows a lot what's going on here, and I particularly really like these two figures here. We see this is looking at it from above, clearly see the gyra, and this here, we just look at the velocities. Flow that is coming at you, going away from you, and it's pivoting around this right here. This is your axis. This shows you the gyra right here. It's beautiful, just absolutely beautiful. So, and then of course, where's the one with the? I also like this one here, showing the very strong halocline, and showing the mixing going on. TS curves are so important in oceanography. So again, the take-home message is that we have a mechanism to help explain how the Barents Sea and the Kara Sea are basically now nearly ice-free year-round. It's getting very close to that point here. And now, if you got this warm water, which keeps getting warmer, by the way, coming in through Fram, and then a part of that gets entrained in that trough there, creating that gyre, we now have a mechanism as to why the Barents is becoming ice-free nearly the entire year, and the Kara not too far behind it. And that at the same time will explain why the Laptev Sea, as far as it becoming Atlantified, is being delayed a little bit. So, fascinating paper. I thank you for your patience and putting up with my blathering away here. But, it's not too often I get to do a deep dive with you guys that, it shows you some wonderful science being done, and just absolutely incredible, excellent work here. I hope they follow up on this with further updated papers as they go out and gather more data and fine tune this. But here we have it. A little gyra, just a tiny little gyra, but it's enough to concentrate the heat. It spreads, keeps the ice-free season longer. Amazing. So, I thank you for your time, and until we speak again, take care.